In this video series, we're going to be looking at how to use the three major periodic table trends, that being atomic radius, ionization energy, and electronegativity, in order to make predictions about how some elements will react with other elements and how some elements will actually react more easily than others. Now, to start this, we're going to start with the simplest possible type of chemical reaction, that being synthesis reactions, where we take a metal and a non-metal and we react them together in order to produce relatively simple ionic compounds, that being sodium chloride and aluminum chloride respectively, and you can balance these reactions on your own time, because what we're interested in is exploring the difference of why one of these reactions occurs more easily or faster than the second reaction. Now, this is not really a concept that we've explored previously, but we can use the three main periodic table trends in order to predict not only that one of these reactions will occur more easily, but which one is going to. So, take a second. Which of these two reactions, number one or number two, do you think will occur more easily than the other, given that the only difference between the two is the choice of metal involved in the reaction? During that time that you've had to think, if you said that reaction 1, the reaction involving sodium, occurs more easily or faster than the reaction that involves aluminum, let's talk about why you might have said that. So the first consideration that we can look at is simply by looking at the number of valence electrons that each element has. Sodium has 1 and aluminum has 3. So therefore, Na has a smaller number of valence electrons than aluminum. Now, both of these metals are going to form cations. Sodium is going to lose one of its electrons, or rather its only electron, in order to get a charge of positive 1, whereas aluminum is going to lose 3 electrons in order to get a charge of positive 3. Now, losing one valence electron is naturally easier to do than losing 3, because it only needs to lose one of them, whereas aluminum needs to lose each of them individually 3 times until it has lost all of them. So right there, that should tell us that sodium is going to react with chlorine more easily than aluminum is, because it only needs to lose the one electron that it has. But if we use atomic radius, we can find an even stronger justification for that. So if we take a look at where each of the elements is on the periodic table, we see that sodium is here, atomic number 11, and aluminum is here, atomic number 13. Why does the atomic number interest us? Because the atomic number talks about the number of protons that each element has. So once again, sodium that has 11 has a smaller number of protons than aluminum does at 13. And the number of protons is going to affect the atomic radius of the element. So because sodium has a fewer number of protons than aluminum does, its nucleus has a weaker ability to attract its valence electron, and therefore its valence electron is going to be even farther away from its nucleus than aluminum's valence electrons are. Let's draw them kind of approximately like that. And because sodium's valence electron is farther away from its nucleus because of the weaker nuclear charge, that means the attraction between the nucleus and its valence electron is weaker, and therefore the farther away the valence electron is, the easier it is going to be to lose. And therefore, if we compare ionization energy of the two, sodium yet again has a lower ionization energy than aluminum does, meaning that it takes even less energy to lose its valence electron compared to aluminum. So no matter which periodic trend we use in order to justify it, it certainly looks as though the sodium reaction occurs much more easily than the aluminum reaction. Now, what if we were to take a look at the sodium-aluminum comparison in a different type of reaction? So here we can see that sodium and aluminum are going to be our element, and the opposite ionic compound, so sodium reacting with aluminum chloride and aluminum reacting with sodium chloride, this is going to be our BC, and if we do a single displacement reaction, we would have sodium and aluminum switching places in order to give us sodium chloride and aluminum, and vice versa with aluminum displacing sodium in order to give us aluminum chloride and sodium metal. The problem is that one of these reactions does not actually make any sense. Now, as we have just established, because sodium is better at losing its valence electron than aluminum is, meaning that sodium is more likely able to give away its electron to chlorine, we can say that sodium is the more reactive of the two in that it loses its electrons more easily and is therefore able to form an ionic compound more easily than aluminum is. Therefore, is it likely that a more reactive metal, a metal that can lose its valence electron and become charged even more easily than aluminum is it likely that sodium would be able to replace aluminum? Well, that would be yes. If sodium loses its electrons even more easily, it can more easily form an ion like this and displace the aluminum metal out of the ionic compound structure. The opposite, however, is not true. If sodium loses electrons and forms an ion more easily than aluminum, then aluminum, being less reactive than sodium, is not able to do the same thing because sodium will simply ionize before aluminum is able to, and therefore it is unlikely that sodium would be able to be replaced by aluminum. What we have here is the beginnings of something that we call the study of elemental reactivity, which is simply a comparison of which element is more likely able to form an ionic or potentially covalent compound over another element. And in the next video, we're going to use what we have explored about the relationship between atomic radius, ionization energy, and electronegativity, as well as things like valence electrons, in order to analyze a number of patterns that we see in both nonmetal and metal reactivity in order to give us a tool that we can use to predict how synthesis reactions and single displacement reactions are more likely or unlikely to occur based on an element's reactivity.